Let us start with the basic definition of fracture or basic description of fracture in ceramic materials. Now, ceramics are widely known as brittle materials. Ceramics have covalent bonding. So, ceramics have covalent bonding, that is their interatomic bonding, and also ionic bonding. So, that why the ceramics are brittle, that lies also in the, or that lies primarily in the characteristic bonding structure of this particular materials. Now, bonding in a very fundamental level can be described by this kind of spring model. Now, hypothetically, if you see that if you load this ceramic under tension with sigma, so these springs they get extended along the direction of the tensile forces, right. So, this is the interatomic distance A prime or A naught, that is the original interatomic distance or initial interatomic distance. Now, as these springs get stretched, so it so happens the interatomic bond distance also increases with time. At a critical stress level, what happens? At a critical stress level, what we call as a fracture stress, this particularly these springs like structures what I have described in the beginning, that get broken, and once they are broken, then cracks can pass through, go through the materials, leading to the total fracture of the materials. So, ceramics are very tricky materials, this fracture is very important to understand. So, now if you look at in a more detailed manner that why this fracture takes place. Now, if you have edge crack, right, if you have edge crack, around the crack tip there is a stress concentration. What is the meaning of stress concentration? That if you apply the stress sigma everywhere remotely from the crack, it is all sigma, but if you go here it is not sigma, right. The stress at this red circle region is certainly not sigma. So, it is elevated. So, sigma is not sigma. So, the stress is not sigma, it is elevated, and this elevated stress level if you can describe as sigma max, right, and then sigma max is essentially related to the crack length, that is C, and also related to radius of curvature, right, sigma into C and comma rho, rho is the radius of the crack tip. So, and typically sigma max is equal to sigma square root C upon rho. That means, longer the crack length and finer the crack tip radius, more is the stress concentration. So, compressive strength I have mentioned, that is typically load divided by area. In one lecture I have clarified to all of you that ceramics are much better under compression compared to tension, and it really outperforms metals in terms of the compressive properties, compression properties. And one of the thing that one has, I want you to recall that I have mentioned very categorically, the compression strength of ceramics is around 8 times larger than that of the tensile strength. Now, if you look at this, what happens during tension? If there are cracks which are distributed very randomly in ceramic, then this crack which are most favorably oriented perpendicular to the stress axis, tensile stress axis, those cracks will essentially propagate, leading to the complete fracture of the materials. Under compression, the cracks which are oriented most favorably towards the compression directions or very near in terms of the angle to the compression directions, those cracks will essentially propagate leading to the fracture. So, for example, these are like secondary cracks which will be generated. Now, these secondary cracks will lead to the fracture of the materials. So, this is like compressive failure. Third one is the flexural strength, that is the 3-point bending. In the 3-point bending, what it means that, for example, this particular flexural sample, this is resting on two support rolls, right. On the top, through this one that you apply the force. So, if it is P, then 2 reaction force is the P by 2 P by 2, right. According to Newton's law, every action there is an equal and opposite reaction. And if you do simple mechanics of materials, like if you consider this is a flexural bar and this is a neutral axis in the flexural bar, and this is under 3-point configuration, right, flexural configuration P and P by 2 P by 2. The stress at any plane which is at a distance y from the neutral axis can be described by this Bernoulli's equation, sigma by y is equal to m by I is equal to E by R. So, sigma is the stress at a distance y from the neutral axis, m is the bending moment, I is the moment of inertia, second moment of inertia. So, it depends whether it is a rectangular cross section sample or cylindrical or circular cross section samples, accordingly you know that I value is different. E is the elastic modulus of the material and R is the radius of curvature. So, under the flexure the material bends and then this particular curvature is typically R. So, first set of equations sigma by m by R is used to arrive at fracture strength is 3 PL divided by, so L is your length between two rolls, okay. B by D square, B and D are essentially dimensions of this rectangular cross section samples. So, this is like you know how it is done. So, there is a two type of testing configuration is possible, 3-point and 4-point testing. So, this 3-point and 4-point testing, their bending moment diagram, also if you look at this bending moment diagram here, so it is like this, it goes to increase, and here bending moment diagram is somewhere like this. So, it is a uniform bending moment where this, so this is your bending moment m and this is the distance. Okay. Now, mechanical properties of polymers. Now, polymers they can be either crystalline or amorphous. Now, typically for metals, what happens that I have shown you that in the description in the very beginning of the lecture, I think when one of the previous lectures I have mentioned these atoms are organized in 3 dimension in regular periodic manner, right. So, the concept of crystallinity in case of metals and concept of crystallinity in case of polymers are very different. So, in metals crystallinity essentially refers to the way the atoms are organized in 3D space. In case of polymers, crystallinity essentially refers to the way that polymeric chains are organized in a local region in a very regular and periodic manner, because polymers essentially means you have a Mar units and you have a many Mar units. Okay. Now, crystalline materials have molecules arranged in repeating patterns and amorphous materials have molecules organized random manner, and in most cases amorphous materials have no long range order, but may have limited short range order, and crystalline materials have both long range and short range order. And morphology of the most polymers are essentially semi-crystalline. So, what it means, they have amorphous domain and they have crystalline domain. So, these polymers, for example, if you consider this this top part, this particular polymeric chain is organized in a parallel manner, right. So, essentially this is more crystalline polymer, but this part is amorphous region, right, this H part. In amorphous polymers, all these chains are essentially in a very disorganized manner. So, there may be in limited manner some short range order, in some part are very microstructurally small parts, these chains are organized in a parallel manner or organized manner, but otherwise this polymer is essentially amorphous in nature. This is a classic example of semi-crystalline polymer, the way this schematic is mentioned here. So, which is the crystalline part? The way I am trying to enclose this particular area with a dotted circle. So, where all the chains are parallel to each other. So, this is like a crystalline part, this is like a crystalline part. So, this is like a crystalline part. So, this is like a crystalline part. So, except this part, except this some of these marked regions, everywhere else these polymers, these materials have very disordered region. So, these are like amorphous region. So, this particular amorphous solid is formed when chains have little orientation throughout the bulk polymer. The glass transition temperature is the point at which the polymer hardens into an amorphous solid, and this term is used because the amorphous solid has properties similar to that of the glass. Okay. Now, although this has been mentioned to you in a very briefly in one of the earlier lectures, that polymers, they have a unique property that is called viscoelastic deformation property. I will come back to this viscoelasticity also when I will be explaining to you some part of the rheology. So, it is a viscous liquid and elastic solid. So, it has a linear elastic region. So, the slope of this linear elastic region is the elastic modulus, and it is followed by yield strength and then constant deformation at a extended deformation at a constant load, and then followed by some increase then leading to failure. So, this what we call plastic deformation, it is more essentially described by viscoelastic deformation. Okay. So, this is the typical characteristics of this polymer deformation. Mechanical behavior of polymers. So, if you consider this is a tensile sample, is a tensile backbone dog bone type of samples, where polymer chains are distributed around this along this backbone chain. Now, what I am trying to tell you is that if it is pulled in tension, what you notice from this to this position, some chains are being organized along the direction of the force. And subsequently, if you see these chains, this is essentially all parallel to the direction of the tensile stress direction. And therefore, this deformation behavior allows the polymer to crystallize, because this crystallization here is essentially referred to the localized organization or reorganization of the polymer chains to give rise to a more regular arrangement of these chains in a microscopic domain. and in this microscopic domain, this is here what we call is the neck region, and this neck essentially extended slowly along the entire length of this polymer sample, and this gives rise also to the time dependent deformation or anelasticity in the polymers, and that this also explains why polymers undergo kind of extended deformation at the constant load or constant stress. So, this is more about this. I think with this we will complete that kind of mechanical behavior of materials, and now I am going to start with this materials material structure, how you can determine the material structure, because in the beginning of the last lecture I have mentioned that structure property correlation is the central theme in this entire materials or mechanical in the entire material science. So, I have described, I think, to a significant extent on the properties. Now, let me discuss about this materials structure. So, let me change my file. This is as I just mentioned that we will start with this material structure characterization, and this structure characterization is very important because structure property correlation is the hallmark in material science. So, before I go on describing that different structure characterization, this is the conceptual tetrahedron: processing, structure, property, performance tetrahedron. Processing means to provide desired shape using mechanical or micromechanical, thermal and mechanical or chemical routes. Structure means it is more macro and micro structure of the materials. Properties is more of the mechanical and functional properties, and performance is more on the efficacy of a material for engineering applications. That is how performance is determined. So, packing of materials. Now, packing of atoms, if you look at this, how this in 3-dimensional space these atoms are packed together. Now, you have this first layer of atoms where all in this particular plane all the atoms are packed together. Now, you will find that when you do this, there are some void space here. This void space, actually these red circled atoms are being placed. Now, when you do these red circled atoms, then you will find there is some void space here at where 3 red atoms are present, and that is the space when yellow atoms are being placed. So, these are like this is like one of the unique ways of organizing atoms in 3-dimensional space. But there are several such unique ways, unique distinguishable ways these atoms are packed in 3-dimensional space, and this particular atomic arrangement or organization leads to lattice structure, and also this is defined by the unit cells and so on. Now, how you can characterize the structure? One of the techniques that has been used for decades is X-ray diffraction. So, you take monochromatic X-rays, these monochromatic X-rays are essentially diffracted by these atoms, and these atoms will diffract, and then several such monochromatic X-rays comes with a particular wavelength lambda, and then if you have this angle of diffraction theta, and if this is that interplanar distance DHKL, then Bragg is the scientist who solved this basic theory, and then he has come up with n lambda is equal to 2d sin theta. So, what is d? D is the interplanar distance. What is HKL? HKL is a plane. In typical material science, you can essentially define different planes by Miller indices, and this HKL is essentially Miller indices. So, what are X-rays? These are beams of electromagnetic radiation. This is short wavelength and high energy, and it is what is wave? It is like sinusoidal oscillating electric field with at right angles to it and a magnetic field. So, it is described essentially lambda, nu is the frequency. So, it is photon energy is typically E is equal to h nu. These are like very basic fundamentals that you remember from the physics. And what is X-ray used for? Determination of crystal structure, also unit cell dimensions, determination of grain size and strain, and typical metals, typical samples which are used like metals, ceramics, glass and various materials. So, diffraction is essentially X-rays to experience positive interference in crystal, that is called diffraction, and this is in a more textbook type of definitions, that when a periodic array of objects, if I go back to this particular drawing, schematic drawing, a periodic array of objects like this is essentially atomic plane, right. So, these planes of atoms, when the periodic array of objects each scatter radiation coherently. So, that means each of these atoms essentially will scatter this extra radiation in a coherent manner. The concerted constructive interference at specific angles is called diffractions. I underline specific angles, I underline constructive interference, and diffraction in crystalline materials is best described by Bragg's law, which I have just introduced you in the last to last slide, is n lambda is equal to 2d sin theta. So, and this for positive interference to takes place, the path difference must be equal to one wavelength or multiple wavelengths. So, n is the order of reflection in this, and here it is clearly shown that X-ray is in phase. So, n is essentially order of reflection. Okay. So, this is a typical X-ray. So, if you have the y along the y axis, it is the intensity, and along the x axis it is the 2 theta. What is theta? Theta is the angle of diffraction. So, you will see that when it is recorded in a machine, not is as fast as you see here, but it is fast enough depending on what is the scan speed and what is the step size and so on and so forth. You get, this is called background intensity. Now, then at 2 theta is equal to 20 degree or so on. So, there are certain characteristic peaks are coming, right, and these peaks are essentially determine some of the crystalline phases in the material. So, depending on what is the intensity of the crystalline or intensity of the X-ray, this is called characteristic peak. So, an X-ray diffraction essentially described by two things. One is the background intensity, one is the characteristic peak, their position and also their intensity. And you will see there is a multiple such peaks are there, right, and these peaks are to be indexed, and thereafter there are ways that how to assign them to a specific materials or metals, or and these materials can be either metallic materials or ceramic materials or composite materials and so on. This is the background intensity, and then second one is the peaks at certain angle with certain intensity, as I mentioned, resulting from positive interference of X-rays with crystal structure of one or more minerals. Minerals can be either materials, different materials. Now, what is the how, as I said that X-rays also can be used for measuring strain and so on. So, one such example has been shown here. For a particular crystal lattice, when it is unstrained conditions, it will give a characteristic peak. Now, when the material undergoes strain, these can be essentially shifted towards the more on the left, or there is a strain induced peak broadening. So, what I am saying, one is a shifting of peak and one is a broadening of peak. Both essentially may signify that the material has undergone strain. I use the word may carefully because it can have another reasons that why this peak broadening can take place, and that is because of the particle size. But if you know the condition of the samples that you are testing using X-ray diffraction, and if you know the material has undergone deformation and then suddenly you see that the material that particular peak has been shifted or peak has been broadened, then you can attribute that kind of peak broadening, peak shifting to deformation of the material. This is one such examples in the annealed brass. So, in case of annealed brass, if it is rolled and then subsequently after that it has undergone heat treatment 200, 250, 300, 3 up to 450 degrees Celsius. In the annealed brass, if you see that since it has undergone deformation, there is a very clear peak broadening. 200 also it is peak broadening is there, and then suddenly at 250 onwards that when annealing is getting the strain is getting removed. This is for the all this slowly the strains get removed, then you get very characteristic peaks of this brass. So, X-ray diffraction, the summary is that it is a non-destructive technique that is used to identify the crystalline structure and composition of a material. This X-ray beam sample, it is a transmitted beam and diffracted beam, and Bragg's law of diffraction that you can get from this figure, that CB essentially C and B is essentially is equal to BD is equal to D sin theta, and path difference between ray 1 and ray 2, that is essentially delta. So, delta is equal to CB plus BD, right, and if CB is D sin theta, is D sin this 2 D sin theta. So, path difference delta is equal to n lambda, where n is equal to 1, 2, 3, 4, and this is the 2D is equal to n sin theta. So, this essentially shows that how this Bragg reflection takes place. For every diffracted beam there exists a set of crystal lattice planes such that diffracted beam appears to be reflected from that set of planes. Okay. Then move on to the electron microscopy of materials. These are used to image the microstructure of the materials, whether it is metals or polymers or ceramics, all the different materials can be imaged by different electron microscopy techniques. So, first and foremost things is that you need to know that what are the different characterization techniques and what information you can extract from these characterization techniques. There are certain abbreviation has been used in this particular slide, that is TEM stands for transmission electron microscope, ACM stands for scanning electron microscope, FIB stands for focused ion beam. So, for all these additive manufacturing courses, I think perhaps if you know more of scanning electron microscope and little bit of transmission electron microscope, that is good enough. And I have already mentioned about your X-ray diffraction. So, these three techniques more or less are useful to characterize that additively manufactured course samples or components or parts. Now, what is the detection range in this additively these different techniques, and what is the analytical spot size? So, in X-ray if you see the spot size is fairly high, it is more than 100 micron. Now, if you go to ACM and so on, the spot size is relatively low, that is kind of almost like 100 nanometer and so on. And detection range like atoms per centimeter volume of these atoms that you can detect, and these you can see this is that very high, that 5 into 10 to the power 21 atoms per centimeter cube, this you can essentially detect. So, it is almost like 10 atom percentage that can be detected in this one. This is like different characterization techniques and what kind of information that you can obtained from these characterization techniques that has been mentioned. So, you can see this scanning electron microscope, it is used for up to 1 nanometer resolution and elemental mapping down to micron, few micron thick. Then there is a transmission electron microscope, this morphology elemental mapping at up to atomic scale resolution. Then you have X-ray diffraction, that is a crystal structure and material modification of phase diagram of the solids that has been also. So, if you look at this particular 2-3 different techniques, this should be enough in the particularly in the context of additive manufacturing of materials. Now, scanning electron microscope, as the name suggests, you use electron beam, and this electron beam essentially, so this is a accelerated electron beam, and it is typically accelerated around 20-25 kilovolt. So, this is a stage, and here your samples are kept. So, you can see this is the door through which actually you can push these samples inside the microscope chamber. So, this chamber is kept under tight vacuum, right, and this is your electron beam line. This electron gun is here, and you have either tungsten filament or lanthanum boride filament lap 6, and you have a GAN alignment control and pneumatic airlock valve. You have at different path of this electron beam, you have a condenser lens, you have an objective lens, and so on. And as these particular lenses are magnetic in nature, so these are like magnetic lenses. It is not like a simple lenses that are used in the optical microscope. And then it is a motorized stage. This motorized stage actually is used to have a control of the sample movement. You can do in the mostly X, Y, and Z movement. So, Z movement is restricted because that is the working distance between the beam and then objective lens and then sample. So, that is typically kept at some specific value like 10 millimeter and so on. So, from scientific standpoint, it is important to understand the electron beam material interactions, which are essentially very important, which is very important to get to know that what are the information we can get and what is the typical interaction volume. So, if you have in electron beam, E beam, and when the electron beam interacts, then it is having a PR shaped interaction volume. And this PR shaped interaction volume, in the beginning they release the secondary electrons, and then there is also primary backscattered electrons, that will give you atomic number contrast and some information, but secondary electrons mostly topographical information. Your X-rays will give you through thickness composition information. But here there is a catch, this X-rays that will be emitted, it will certainly not give you very reliable information if for the low atomic weight element like oxygen, nitrogen, carbon, and so on. But for larger atomic weight element, this will give you quite good reliable values. Now, this interaction volume, if you see this incident electron, the interaction volume, this is called PR shaped interaction volume, and this PR shaped interaction volume that extends quite a few microns into the depth. So, if it is a 10 nanometer, this is a principal beam size, this interaction volume, this is a width of around 1 micron, and there is also depth to which this will operate. And this is the secondary emission range, secondary electrons and backscattered electrons and X-rays, which I have shown you before. So, transmission electron microscope, again it is a high energy electron beam. So, it can go to 200 kV up to 300 kV or even some of the most modern microscope, you got 300 kV electron beam that is used. So, this is the typical electron path, how it goes, and you can see that constantly this electron beam goes and they are being guided using a different kind of magnetic lenses like condenser lens, intermediate lens, project. So, you have a condenser lens, you have objective lens, and you have intermediate lens. And there are different image planes that are also being mentioned, like object plane, the first intermediate image plane, this is secondary, second intermediate image, and so on. And finally, you see that image here, this is the viewing screen. So, this is you are talking about this viewing screen. Through this viewing screen, you can look at this image very carefully, and also you can get the diffraction pattern, which can give you an alternative way to essentially analyze the materials microstructure. So, electron beam interactions also has been described here. You have the incident high energy electron beam, as I said, that 200 kV or 300 kV electron beam, and then this goes through direct beam. There is elastically scattered beam and there is a inelastically scattered beam, and they have a secondary electrons, characteristic X-rays, those you have seen in the earlier slides in this particular lecture. And these are like different signals which are generated when high energy beam of electrons interacts with a thin specimen. So, it is indeed important to use SEM and microcomputer tomography, which I have also mentioned in one of the last lectures, few lectures. And this microcomputer tomography, they use X-ray beam, but this X-ray beam typically is around much higher than that of the X-ray diffraction. It is like 70 kilovolt, and your samples like 3-dimensional, let us say additive manufactured porous scaffolds are being there. So, this particular sample holder will rotate, right, and if it is rotates, the X-ray beam continuously falling, then you get 2-dimensional slices, and these 2-dimensional slices, they are stacked up and they get a 3D image. So, this brings me to the end of this lecture on materials characterization. So, what I have not shown you, but perhaps that would be important in some specific cases, is the surface topography, like additively manufactured part, how to make the surface topography. This is very sophisticated atomic force microscope, but normally you can use some of the other like optical perimetry and so on that you can use for the surface topography. I have already shown you some microstructure and phase assemblies, that is good enough for additive manufactured. In case of surface chemistry, XPS, FTI or Raman spectroscopy, that is not something very widely used, regularly used for additive manufactured, but just to give you a complete idea, there are also several other techniques which are used for materials characterization. Since it is not a course on material science, I am just showing you this last slide just to show you that in case of other material science courses, an instructor professor may teach you on how to measure the mechanical magnetic properties, how to measure the electrical properties and surface chemistry. So, this brings me to the end of the materials characterization. Thank you.